We now consider example 2. We have a mixer sitting on a platform that's supported by two members AB and CDE with a spring connecting D and B. We can see immediately the role played by the spring in this problem. In its absence, the rectangular configuration of members AB, CA, and CE is the kind of unstable assembly we mentioned in section 6.3. In the absence of a spring, the whole assembly will rotate counterclockwise and slam into the floor. If the spring is really stiff, it may exert such a large restoring force at D that a substantial normal force must develop at H in order to keep the assembly in equilibrium. Therefore, the minimum spring force needed to support the mixer is one where we are on the verge of breaking contact at H, and the normal force there goes to 0. There are two force members in this problem, member AB and spring BD. Unlike our first example, it doesn't help us much to draw a free body diagram of the whole assembly, as we'll have 4 unknown forces between the two pins at B and E. Instead, our focus will be on the mixer and its platform as one free body diagram, and member CDE as a second free body diagram. So our isolating surfaces here will look like this, and then for the mixer and platform together, and then we'll be looking at CDE here as a second free body diagram. So this will be 1, and this will be 2. There's no need for us to actually represent the detailed geometry layout of the mixer on the platform. All we really need here is the appropriate location for the center of gravity relative to the platform. So for my free body diagrams here, for 1, I'm simply going to represent the top of this as a straight line. The key issue is the connections at A and B. So for A, we'll have a force from the two-force member FAB, which I'm going to represent as being in compression. And we note that once again we have an orientation here that corresponds to a 3, 4, 5 triangle. So I'll represent that here. The figure is a little misleading in that the distance here between A and C is 16 centimeters. And the center of gravity is shown as being a distance 10 centimeters from A, which would actually put it roughly over here somewhere. So this is going to be my weight. And that's 10 centimeters from A. Then we have a pin support at C. And I'll represent these forces CX and CY this way. That's our mixer platform free body diagram. For CDE, we have first the equal and opposite forces from C. So if on CA, CX and CY are as shown, they're equal and opposite on CDE. So CY is like this, and CX is like this. For the spring, that again is treated as a two-force member. Its geometry is not quite as clean as the 3, 4, 5 triangle. I'm going to go ahead and represent this as FBD Here the spring is in tension, so it's pulling on CDE. And you'll notice from the geometry of this that we have a rise over run of 8 over 22. That doesn't give us a clean integer value for the hypotenuse. This is going to be the square root of 548. And then we have a pin support at E, so we have EX and EY here. And you'll notice our distances here are, we have a horizontal distance of 12 centimeters here and a vertical distance of 16 centimeters here. Okay, so before we proceed past this point, let's just take stock of what we have and look at the solution we need. We're ultimately interested here in finding FBD, this minimum restoring force of the spring. So let's make a note that the number of unknowns that we have consists of CX, CY, FAB, EX, EY, and FBD. That is, we have 6 unknowns, we have 2 bodies, we can write 3 equilibrium equations for each one, so we should be able to solve for all the unknowns in the problem. In this case, we're only asked for the restoring force of the spring, so we may not need to use all of those equilibrium equations, and we can establish a procedure for getting there as efficiently as possible. So what we'll need to do is to start with free body diagram 1 and use all the equilibrium equations to solve for the first 3 unknowns, CX, CY, and FAB. And then we'll go to free body diagram 2. At that point, having CX and CY, all we really need to do is impose moment equilibrium, take some of the moments about E and set that equal to 0, and at that point we should have enough information to get FBD. So that will be our procedure in solving the problem. So we'll go first to our first free body diagram, and we'll solve for the force and 2-force member AB first. We'll take moments about C and set that equal to 0. We have just the vertical component of FAB, which is exerting a moment about C, and it's exerting a counterclockwise or positive moment, so we have 4/5 FAB times 16 centimeters. And then the weight is exerting a clockwise or negative moment through a moment arm of 16 minus 10 or 6 centimeters, so we have 8 kilograms times 9.81 meters per second squared to get a weight in newtons times 6 centimeters. That equals 0. We might just note here that the weight here turns out to have a value of 78.48 newtons. So if we solve that for FAB, we end up with a value for FAB that's equal to 36.79 newtons. And then we can use force equilibrium in X and Y to solve for the forces at C. We have CX minus the horizontal component of FAB, which is 3/5 FAB equals 0, and that gives us a value for CX that's equal to 22.07 newtons. We have CY in the vertical direction. We have CY plus the vertical component of the 2-force member, which is 4/5 FAB minus the weight equals 0. And that ends up giving us CY is equal to 49.05 newtons. Now we can go to our second free body diagram and take moments about E and set that equal to 0. And we can see that we have positive moments exerted by both CX and CY. CX is exerting a moment through a distance, a positive moment through a distance of 16 centimeters. CY is exerting a positive moment through a distance of 12 centimeters. And then we have two contributions from our spring restoring force. The vertical component is also exerting a positive moment. Its sign is 8 over root 548. So there's the vertical component of FBD, and it's doing this through a moment arm of 6 centimeters. And then the horizontal component is exerting a clockwise moment, and it's doing so through a distance of 8 centimeters. So the cosine is this value. Here's our horizontal component times 8 centimeters is 0. So our expression then, we can rearrange this for FBD. Using our values for CX and CY, we have 22.07 newtons times 16 centimeters plus 49.05 newtons times 12 centimeters over this collection of terms, and that number turns out to be 172.2 newtons.